Good evening, everyone. So, welcome back to another session. So, today we will continue the journey of with Mohamed, who will be taking us further into the classification of phases of matter using machine learning. So, in our last session, we covered the basics of neural networks and implemented them using PyTorch. And I hope you've been practicing. So, as always, remember to mute yourselves during the talk in order to minimize the background noise. And also, if you have a question, you raise up your hand and you ask the question. So, welcome, Mohammed, to today's session. So, I would like to hand over to you so that you start the session.
Thanks very much, Henry, for the kind invitation
You're welcome.
again. It's a real pleasure to be here. So today we're gonna dive into like the application of machine learning to physics, more specifically, the classification of phases of matter using machine learning. But before doing so, I thought it would be good to share a bit of the technical details of the feed-forward neural network, since we just covered the high-level details, not the fine details of the mathematical, how it works in terms of mathematical equations. So that's what I wanted to cover in the first part of this lecture. Just a brief overview about the mathematics of feed-forward neural networks. The purpose is not to scare you with the formulas, but just to give you an idea for those who are interested about how these architectures work. And if you're interested, you can read more after the session. And also in the first hour of this session, I also wanted to talk a bit about how we can use machine learning to classify the phases of matter of one model called the 2D Ising model. So I'm going to talk about this model more specifically also in the first hour. And if we get to that, hopefully, then in the second hour, we're going to have a hands-on session on PyTorch again, where you're going to practice again on Google Colab, similarly to last time. And you're going to do this in real time so you're going to basically do the classification of the phases of matter of this model using the feed-forward neural network architecture that we've seen last time. Okay, so far so good. Okay, so if there are no questions from last time, I guess we can get started with the first part in terms of the mathematics of the feed-forward neural network. But at any point during the lecture, please feel free to stop me by unmuting yourself, or I guess I'm not going to be able to see your questions on the chat, so it would be better if you unmute yourself and ask me any question you have. Okay. So just to remind you about what we've seen last time. So the feed-forward neural network architecture belonged to the class of neural networks in the field of deep learning, which is a subfield of machine learning. And we've seen that this architecture has an input layer and also an output layer. It doesn't have to be one-dimensional, but it could be also multi-dimensional with multiple nodes. And we also have a hidden layer. And it doesn't have to be one, it could be also many layers. And the purpose of this hidden layer is to have some sort of learnable features. If you remember the example of predicting the probability of a phone being a top seller, having these kind of hidden features allows to build a more expressive model to do a better prediction. And these connections are learnable, like these are the parameters that we're tuning during the optimization. And the fact that we are using hidden layer allows to drop this feature engineering in such a way that in case we don't know what are the relevant features in our data, this neural network architecture will be learning these features without a need for us to learn these features or to input these features in advance. And we've seen that this architecture can have many layers. So we can, instead of having like one hidden layer, we could also have two hidden layers or even more. And we've seen like that this architecture can reach even hundreds of layers. And this is like what makes the power of neural networks. They can actually be very deep. And that's one of the motivations of this term called deep learning, because that's what the depth in this architecture is actually what makes these architectures sometimes very powerful in real world applications. Now, in terms of the math, so this is what I wanted to cover very briefly. But if you feel that you're lost during this part, it's okay. I can recommend some references that you can read later. Again, the purpose is not to master this part, it's just for you to explore how this works how these architecture work more concretely. So here in the first part, like in the first layer, we have what's called the input layer, where basically what we do is we input some vector X. So this could be a picture with pixels, or it could be a sentence of words, or any other types of inputs. So in terms of physics, this could be, for instance, like a configuration of physical degrees of freedom. So if you have heard of the spins in quantum physics, the spins can be either up or down. So like a system of spins could be as an input to this architecture. And the size of this hidden layer is given by the size of the vector, and we can call that N0, okay? So N0 is the number of neurons in the input layer, okay? Now, in terms of the hidden layers, we can also call N1 to be the number of neurons in the hidden layer. So, and we can also call the vector, so basically each neuron will contain a number, and we can store all these numbers inside this vector, okay? Yeah, if I'm going too fast, please let me know so that I can go more slowly. So now, also in the second layer, we could also have a different number of layers, N2. And these N1 and N2, those are hyperparameters, meaning that we can tune them. So I'm sure you've seen this last time in the tutorial on PyTorch. You have this ability to tune the hyperparameters. So those are hyperparameters we can tune, but N0 is fixed by the dataset. So it's already fixed by the number of components that we have in X. In terms of the outputs, we can call that N3, which is a number of neurons in the output. And we can call this outputs vector Y. And the number of neurons in the output would depend on for instance, on the number of classes if we're dealing with a classification. So if we have, for instance, 2 pictures of cats and dogs, then we have 2 kind of predictions. So that's why we have 2 outputs. But if we have, let's say, other types of classification tasks, let's say digits, like between 0 to 9, then we need 10 classes. So we need 10 of these neurons on the output, okay? So it doesn't have to be always 2. And if we're dealing with some sort of regression where we need to fit some sort of curve or predict some sort of continuous parameter, then we can only have 1 neuron at the output, okay? So those are the different the scenarios that could happen for the output layer, okay? So now having defined this notation, we can dive deeper into how a neuron works. So to do this, I can zoom into the ith neuron in layer number L. So what I mean by this is that assuming that this is layer L, and this is the ith neuron in layer L, okay? So if you look at this neuron here, it's connected to all the neurons in the previous layer, right? And also it's connected to all the neurons in the next layer, okay? So if I transfer this picture, I should see something like this, okay? Okay, so I hope you all agree with this part. Now, what I can recall from this notation that I have before is that, like you see here, that this index 1, for instance, corresponds to layer number 1, okay? And if I do -1, then that will be index 0. So it's the same thing here. So I have layer L, then all the components in the previous layer will have index L -1, okay? And each neuron will go, like the values of the neuron will go from 1 to until NL -1, and NL -1 is the number of neurons in the previous layer. So if I'm here, the previous layer would be this one, okay? And now in terms of the outputs, so this neuron, once it receives information from all the previous neurons in the previous layer, then it's gonna send them the same message. It's gonna send the same number, AIL, to the neurons at the next layer, okay? So this is what's going on, for instance, for this neuron. It's gonna send the same number to the other neurons, okay? And we can call that AL with using the convention we described over here. Okay. So far, so good. Is everyone following me? Okay, so far? Okay. I guess I have a question here. Yeah, okay. So there was a question like that the number of neurons in the hidden layer must be more than the number of neurons in the input layer. Yeah, so that's a great observation. Like sometimes it's good to have more neurons in the hidden layer than the input layer to allow for more expressivity. But sometimes it does not have to be the case. Like sometimes we could have hidden neurons that are the number of hidden neurons in the hidden layer could be lower than the number of neurons in the input layer. And there are some examples of architectures that are successful to do classification or regression, even though that you have a lower number of neurons in the hidden layer compared to the input layer. But this is a great question. Yeah. Okay. Now, since there is the same outputs to the so since the neuron is sending the same output to the neurons in the next layer, then we can basically think of the neuron as some sort of a function, okay? So this is the example we've seen last time with the probability of a phone being a top seller. It's the same thing here. We can think of a neuron as a function that takes inputs of the neurons in the previous layer and that outputs some value, which is AIL, okay? And the way we can do this is by using a linear transformation. So I think that would motivate what you've seen last time in PyTorch. I guess you've seen this linear layer in PyTorch. So that's exactly what's being done under the carpet. So but basically what we do is that we take all the neurons in the previous layer, so those neurons, we do a sum from 1 to NL minus 1. So basically we sum over all of those, and we multiply each neuron by some weights, and we can call that Wij. And then this also weight is dependent on each layer, okay? And this is called a weight, and that parameter is something that we can tune or train using during the optimization of the neural network. In addition to that, we can also define what's called a bias. So that's just an offset parameter that only depends on the index I of the neuron at the current layer, and also depends on the index of the layer that we're currently at. So that the outcome of this combination or this linear transformation is what we can call the pre-activation. And the reason why we call it a pre-activation, we can also denote it by this ZIL. The reason why we call it a pre-activation because we can apply what's called an activation function, or this function JL, which could be some nonlinearity. So I guess you've seen last time that we can use ReLU, sigmoid. There are also other types of activations I'm gonna talk about. I promise you to talk about these today. And once we apply this nonlinearity or this activation, we can go from a pre-activation to an activation. So these outputs of the neuron is called an activation as well, okay? So this is also inspired from the biological property of the neuron. It fires some sort of activation to the other neurons. And since this is a linear transformation, for those who are familiar with linear algebra, we can transform this relationship into a linear transformation. So basically these weights, we can gather them into a large matrix. And the same thing for these biases, we can also put them into like a vector. And we can also put these output of the neurons and also for the neurons in the previous layer into a vector, as we've seen in this example here. So by doing this, we can rewrite this as a linear transformation of the neurons in the previous layer times a matrix plus another vector, and then using a nonlinearity applied element-wise on this pre-activation to get the activations of the neurons that will be sent to the next layer, okay? So this is just a brief overview to kind of explain how the code works in PyTorch that you've used last time. And before moving to the definitions like of the examples of the activation functions, I want to pause for a second here to see if there is any question about what it talks about at the moment. Are there any questions so far so good? Yeah, I won't be able to see them, all the messages, but let me check just one question if there is one. I think it's good. Yeah. So if someone misses this part, it's okay. It won't affect the next part. Okay. But I guess you can always go back to the recording and let me know if you have any questions about this part. Okay. So hopefully if this part is like if it's
Hello, sir.
yeah, please go ahead. Yeah.
Please, sorry, can you go back a little to the
Sure.
previous speech?
Yeah, sure.
You were saying we can create a matrix for
Yeah.
the first one where we have the equal to.
This one?
Yes, the A subscript I.
Yeah, that one?
Yes.
Yeah.
And I'm asking, is that not for a particular neuron?
Yeah, right. So if I'm going back here, then I could denote like this one as A1, 1, this as A2, 1, and this as A3, 1, and this A4, 1, and this A5, 1. Okay, so the index 1 here is for the layer, and the indices is for each neuron in the same layer. Okay, is this part clear?
Okay, thank you, sir.
Yeah, it's a pleasure. So all of these are in this vector here. Okay, this is a great question. Any other question before moving on to the activations? Okay, so if not, so let's go and see some examples of activation functions. So just to motivate also some of the things you were doing last time in the hands-on session in PyTorch. So I'm sure you've seen this activation W, which is basically defined as the maximum of 0 or the inputs Z. So this means that if Z is positive, it's going to be just the identity. If it's negative, then we're going to set all the outputs to 0. Okay. So basically this is a nonlinear activation in the sense that there is a nonlinearity. So it's not a linear function. There's some sort of nonlinearity going on over here. Okay. And the intuition why this works is that sometimes if this input is positive, you're keeping the information. And if this input is negative, then you forget all the information. In some sense, we as humans, we learn by forgetting the irrelevant stuff and keeping the relevant stuff. So somehow this activation allows to do this. So although it's not clear yet, but this is one intuition that could help you to understand why this works. There's also this linear function, which is basically nothing but the identity. So this means that when we are applying this linear transformation, we don't do anything. We don't apply this activation function. Okay, but this turns out to be not useful. Like it's good to use a nonlinearity, and we're gonna go back to that in a second. There's also this other activation called soft plus, which is defined by this relationship. So some people use that as well. There's also other types of activations. So I'm sure you've seen this before, like in the last tutorial. So this is the sigmoid or also the logistic function, which is a function between 0 and 1. So this is helpful, for instance, if you want to predict, let's say, a probability of something. So it's going to output something between 0 and 1, okay? So even though that your input will go from minus infinity to plus infinity, the output will always be going to be between 0 and 1. And sometimes it might be also useful to use the hyperparabolic tangents, which, as you might know, defined like this, which allows to return like an output between -1 and 1, okay? So whatever you put in the input, you're going to get something between -1 and 1. There's also this hard threshold, but it's not a good choice in terms of for practical purposes, because if you can see here the gradients here is 0, and the gradient here is 0, and the gradient here is infinite. So this means that it's not it's not going to be helpful to use this architecture to optimize the neural network, because we're going to be using gradients to optimize the parameters of the neural network. So I'm going to go back also to that point in a second. I'm going to talk a bit about gradient descent and why, and from that point, I guess you'll see why this is not a good choice for an activation. Okay, so this is just to motivate some of the names you've seen last time in that tutorial in PyTorch. And there are also other choices. I would encourage you all to kind of type this in Google or search in papers about other types of activation functions in machine learning. And one last activation I also wanted to highlight is the softmax activation, which is typically used at the output layer. And basically what this activation function does is the following. So let's imagine that I have a vector v1 and v2 and then v3. When I apply softmax on this vector, then I'm gonna get a vector that's normalized to 1. So what I mean by this, so the first input to this vector will be something like this: the exponential v1 over z, exponential v2 over z, the exponential v1 or v3 over z, and z is basically the sum of exponential v1, exponential v2, and exponential of v3. Okay? And why this is a good activation function at the outputs, it's useful since if you sum this, then it should give you 1, right? So, and why this is useful, that's because if you want to predict the probabilities, we know that probabilities sum up to 1. So if you want to predict the probability of something, it's good to have a probability that a sum of these probabilities to be 1, so that you have a well-defined probability. If you're just using a sigmoid, like let's say that you're just using a sigmoid in each neuron, then you're gonna get some number that's between 0 and 1. So you might get here 0.5, in here 0.4, in here 0.3. And these will add up to, you see here, 1.2, which is larger than 1. So it will not add up necessarily to 1. But if you use softmax, then you might be getting something like this: 0.5, 0.4, and then 0.1. And so they will be adding up to 1, and this will give you a better, will give you a well-defined probability at the outputs. Okay, so this is very helpful in case you want to do some sort of classification. And again, I'm sure you'll find it helpful in the demonstration of the hands-on session last time, where we have spirals. So if you have more than once, like if we have like 4 spirals, 5 spirals, and more, it's gonna be very useful to use softmax, and you're gonna see that you're gonna get a better accuracy if you use the softmax activation. Okay. Now going back to the nonlinearity, it's what makes it very useful to use a nonlinear activation compared to a linear activation is the fact that there is a theorem that says that neural networks can be universal function approximators. This means that they can approximate any function arbitrarily well, given that you have a very arbitrarily large number of hidden neurons. And this can be demonstrated using nonlinear activation functions. And if you're just using a linear activation, then you won't be able to, this theorem won't apply. Okay, so this is why nonlinearities are helpful, because we have this guarantee of expressivity. But just one thing I want to warn you about is that it's not always helpful to have a very large number of neurons to get a better accuracy. Sometimes we have this phenomenon called overfitting, which you can see in this simple example where you can fit polynomials. So this is not a neural network, but just an example where we have so we have these data points, right? You see these blue data points, and this is the red plot is a fit using a 9th degree polynomial, which means that it has more parameters than it needs. But if you fit with a 3rd degree or the 2nd degree polynomial with just 3 parameters, then you see that it's going to provide a better fit for this data. Okay, so sometimes it's not always helpful to use more parameters. Sometimes you need to strike a balance. This is sometimes called the bias variance trade-off. Like, you can read more about this in this reference if you're interested. But this is not the purpose of this lecture. I just wanted to tell you that there is this problem in machine learning that you need to be aware of if you want to do some sort of machine learning task. And I also wanted to show you this example in the last demonstration we've done last time. So if you increase the number of neurons to be 20, so it was 4 last time as default. If you do 20, then you'll see something like this in terms of the boundary. So you see some sort of irregularities. You see here, like there's some sort of irregularities, and also here as well. If you train for a long time, then you'll be able to see this plot. And I would encourage you to try this after this lecture. And one way we could cure this is by using a technique called early stopping. So this means that we could stop earlier. So instead of training, let's say, for 10,000 steps, we could only train for 5,000, or stop halfway or quarter away or somewhere in between, in such a way that we avoid these overfitting, so that we can get, for instance, you see in this plot, we have smoother curves. So this way we can avoid this overfitting by stopping earlier. So this is one way we could avoid overfitting. But there are also some other techniques that are beyond the scope of this lecture. So I'm gonna share some references at the end that you can use to read more about this if you're interested. Now, before going to the classification of phases of matter, I also wanted to talk a bit about cost functions. So I haven't talked a bit about how we can optimize neural networks. So I just told you that there is a way to train, but I haven't shown you how we can train. So one way of allowing to train these architectures is using what's called cost functions. So these cost functions are a way to know how close you are to the truth. So what I mean by this is that, let's imagine that I have so my outputs of the neural network is given by the vector at the last layer. So I'm gonna call this index of the last layer capital L, and all the neurons in the output layer are given by this vector here. So if you go back to the very first example that I've highlighted here, then this is gonna be so A3. So for 3 layers, then the output layer is gonna be defined by this A3. So for the sake of generality, let's imagine that this is equal to AL. And then I imagine that I also have some sort of labels, right? Y, that I want in such a way that I want these AL to be as close as possible to my labels Y. So to do this, what I can do is minimize the difference between the two. So one way of doing this is by taking the difference between A and Y, and we can take the error, which is either by taking the absolute value, but a typical choice is by taking the square. And then we can basically sum over. So you can see that for each data point, so for each data point X, we're gonna have an input, and we're gonna also have a label, okay? So for each input, we're gonna get this vector and also this vector for the labels. So I'm talking here about supervised learning where we have labels. So I'm gonna also denote this dependence on X here. And now, since we have, since we want this one to be as close as possible to this one, we want to have that for all the data sets in our data. So we want to have an estimate for all the errors the neural network is making. So this way, it's good to do the sum over all the data points in our data set that we can call D. And then we can, for instance, take the average. So we can do this by dividing by the number of data points that we have in our data set. So we can denote this by this notation here. So a cardinal of the data sets, and that will be the definition of what we can call the cost function. Okay, so this is known as the mean squared error. Or MSE, okay? So I'm sure you've seen this in the tutorial last time. So you've seen this MSE, like activation, cost function. There are also some other types of cost functions that I don't think we have a time to cover them, but in case you're interested to read more about them, like there's what's called the cross entropy. So if you're interested, I can share some references with you later. And you can also use it in PyTorch. So it's already defined in PyTorch if you want to use it. But I guess this is the simpler to understand. The goal is to minimize the difference between the predictions and the true labels. So ideally, you want this to be as close as possible to 0 so that you make sure that the predictions of the neural network are close to the labels. Okay? So far, so good? Does everyone has a question so far?
Hello, sir.
Yeah, please go ahead.
Yes, and Norm, I used to have this question all the time. Yes,
Yeah.
when you look at the AX and the YX,
Yeah.
are those vectors? My question will be: are those vectors? And if they are vectors, what do you get at the end after that operation? Are you going to get a real number, or you are still going to get a vector at the end of that operation?
Very good question. Yeah. So what I'm doing here, so basically when you do like that, so when you do this minus this, you're gonna get a vector, right? But when you do like this is squared. So I'm not applying the square like elements wise on the vector, but it's basically gonna be the L2 norm squared of the vector. Does this make sense?
Okay, yeah, it makes sense. Yeah.
Okay, so maybe like I could be more specific for the other participants. So if I call this vector z, then when I do z squared, so if z, let's say, is z1, z2, and then z3, let's imagine it's a three-dimensional vector, then when I'm doing z squared, this means that it's going to be z1 squared plus z2 squared plus zt squared. So it's just going to be a number. Okay, this is a great point, but I guess it would be better if I denote it as something like this. So that it's clear for everyone. So I'm going to do the L2 norm so that it's the same as this one. It's clear for everyone why this one is the same as this. Okay? Any other question? So far, so good? Okay. So now one question that you might have is, how do we optimize? How do we make this C, this cost function C, as close as possible to the minimum? So this is exactly what's you've been doing in the tutorial last time. Like, so this was implemented in the behind the scenes in PyTorch, but it would be good to see what's going on. So the algorithm that used to minimize this cost function C is called gradient descent, and this procedure is actually very interesting, and hopefully it's going to be easier for you to understand by looking at this simple example where imagine that this neural network has only one single parameter. So this cost function will depend on only one parameter that I can call lambda. And let's imagine that this is some sort of continuous function, which is the case in most of the time. So imagine that we have this some sort of function that has this minima over here, and imagine that we want to find the minimum. Okay, so let me do this case, and let me go to the other cases where there are some pathological cases. So let me do a simple case. So imagine that we have two minima like this, and we want to find the minimum over here. So one way of doing this is by, so first of all, like when we start the machine learning task, we need to randomly initialize the parameters of our neural network. So if we initialize, we could be somewhere over here. Okay, so by just a random initialization, we could be somewhere here in some parameter lambda 0. And then the idea is we want to go downward, right? We want to go downward step by step until we get to the minimum. And the way we go downward is by following the gradients. So we know that the gradients, if we want to estimate if we want to see where the gradient is looking here, it's positive, so it's gonna be like that. So that's the gradient here, and this means that if we want to go downward, we need to. So if the gradient is here, then we need to go to the opposite direction of the gradient. So this means that we have to go to do a step to the opposite direction. So if I have the gradients estimated, so if this is my gradient, dc over the lambda, then I want to have the opposite of the direction of the gradient so that I can update the parameters. So my new parameter lambda that I can call lambda 1 will be equal to lambda 0 minus some sort of a constant that I can call eta times the gradient at lambda 0. Okay? And then I can do this step again and again. So this parameter here, eta, is what's called the learning rate. And one recipe to choose that learning rate is by making sure that it's not too small and also not too big. So what I mean by this is that if this is very big, then you're going to make a very large jump. So you're going to go all the other way, which might not necessarily minimize the cost function. But if you're also making a very small step, then you're going to move very, very, very slowly. So it's going to take you forever to go to the minimum. So it's good to take some balance in between, like to take something in between in such a way that you can converge in a reasonable time. Yeah, please go ahead. I see some hand raised, so yeah, feel free to unmute yourself and ask your question.
I wanted to know, you see, inside the gradient descent graph, are we plotting the width against the cost function?
Very good question. So here, I'm doing a simple example where I only have one parameter or only one weight, okay? But I guess in our networks, we could have thousands, even millions or billions of parameters, okay? So what I want you to see here is that this can be generalized. So that's why I have this partial derivative. Like the C can also depend on other parameters or many other parameters. So we can compute all the partial derivatives and then update the parameters using this update rule by taking minus a positive constant times the gradients. Does it make sense? Does that answer your question?
Yes, please.
Okay, thanks. Okay, so basically by doing this again and again, by updating the parameters by taking, for instance, lambda 2 equal to lambda 1 minus the gradients at lambda 1 times this learning rate, then we'll be able to move this. So you can think of this parameter as some sort of a ball going downwards to the minimum. Okay, so we want to achieve this result here, where hopefully lambda we get here is the optimal parameter that minimizes the cost function. Okay, so before moving to the next part, I wanted to do some sort of quick visualization to see how gradient descent works, and then hopefully that will give us some time to go to how we can use the feed-forward neural networks to classify phases of matter. Okay, So let me share my other screen.
Sorry,
Okay.
sorry, sir.
Yeah, please go ahead. Yeah.
Yes, I have a question on the previous slide.
Sure. Yeah. So let me share
Yes,
my
from
other.
from that,
Sure.
yes, from that graph, it's a good example. Yes, I must I must say that because I can see that we have the global minimum and the local minimum there.
Yeah.
Is there a possibility that whilst looking for the minimum, our gradient descent be trapped um,
Very good
on
question.
that local minimum?
Yeah, very good question. Yeah, this is a great question. Yeah, I like this question. So, for instance, here, let's imagine that we do gradient descent here, then of course we're going to be stuck, right? And that's not good. Well, that happens a lot in deep learning. Sometimes it's okay if you're stuck in a local minima. Sometimes that could lead to still a good performance. But like it's always good to kind of it's always good to circumvent these local minima to obtain the global minima or something that's closer to the global minima. So that's why I wanted to do this visualization, and I hope that would answer your question. So there are actually more sophisticated ways to do gradient descent. So this is the simpler version of gradient descent, but there are more sophisticated algorithms to do gradient descent. So this is what I wanted to share in the demo, but yeah, this is a really great question. Thanks. So let me share that visualization. Okay, so this is gradient descent visualization. I guess if you're interested, you can also Google that, like the name of that software, if you're interested to try it on your laptop. And so basically here I have a different types of optimizers. So there's gradient descent. There's also momentum. So this is another type of gradient descent. There's ADA grad, there's RMS prop, and there's also ADAM. I guess it's not visible here, but it's in dark blue. And those are like these optimizers are kind of variations of gradient descent. I don't think we have time to cover all of them, but if you're interested, you let me know and I can share some references later. But what I wanted to share with you is like how each gradient descent like optimizer, how it's gonna do in these kind of tasks. So for instance, here this is kind of a two-dimensional plot in the case when we have two parameters. And this is the third axis is the cost function value. And you see here that this is the case when we have only one global minimum. So you see here that all the optimizers did well, except this white one, which is going very slow. Okay. Then we can also do the other case where we have a local minimum. So this is exactly was the question that I had very recently. So you see here that the ADAM, which is the dark blue, managed to find the global minimum, but these other optimizers didn't do well. So, and also this AdaGrad is not doing well for some reason, I'm not sure. Okay, so sometimes it's good to try different optimizers in such a way that sometimes you'll find a global minimum compared to a local minimum. If I also try some other landscapes like this saddle points, Adam is going faster and also followed by RMS prop and then momentum, and these other two, like the plane gradient descent that I've showed you just now is not doing it well. So it's actually stuck here. Okay, so the one that I've showed you on the notes is not the optimal one. So it's good to use, for instance, Adam, which is already built in PyTorch. So you can look for that in the documentation of PyTorch, and you can use it. And it's the most I've seen that it's the one that's that's used more often in the machine learning literature, but it's not the best. Like sometimes there might be some optimizer that's best in some cases compared to others. So I just wanted to share with you this demo just for you to see that different optimizers are there and to encourage you to try those in when you're doing machine learning research if you're interested in doing machine learning research in the future. And before going to the hands-on session, now I wanted to talk a bit about doing detection of phases of matter using feed-forward neural networks. So just before going to the technical details, I want to talk about I want to briefly introduce what we mean by phases of matter. So I guess you all know the phases of water. So water can be either a solid at very low temperatures, or a liquid at intermediate temperatures, or a gas at very high temperatures. So this is the typical case that we all know. There's also a less known example, which is the example of ferromagnetism or paramagnetism. So sometimes when you have, so this is the typical case, for instance, of iron. Sometimes when iron is at very low temperatures, it can be attracted by magnets, so it can stick to a magnet. But in some other cases, when we heat it to some very high temperatures, then it can become paramagnetic. This means that it becomes a paramagnet. Okay, so those are two different phases of matter, and those are the examples that I wanted to focus on in the hands-on session today. And these kind of phases are modeled by this simplistic physical model called the 2D Ising model, where this model is defined using spins. So those are spins that you can see here on this 2D grid. So these spins can be either up or down. So here in this configuration, you can see that all the spins are up. And this phase of matter turns out to be a ferromagnetic phase, because all the spins are aligned, and this means that there's what's called a non-zero magnetic moment that allows the material to stick to magnets. We can also have the other case where all the spins also all down. Okay, so this is what I have here in this slide here. So this is also a case where our material can also stick to magnets. So what happens is that I have an energy function where I have interactions between nearest neighbors. And this energy is in such a way that it encourages spins to align to the same direction. So here I have this coupling J, which is a positive number. So I have a negative energy here each time this is equal to +1. Okay, so this is equal to +1 if both of these are +1, which is these cases here, or both of them are -1, or both of these spins are down. Okay, so the energy is minimized when all the spins are up or all the spins are down. Okay, now this is typically the case when we don't have external influence, or what we can also call temperature fluctuations that come from the environment. So this is what happens when we have temperature. So when you have temperature, you get some sort of disorder. So temperature basically encourages spins to flip at a random rate. So if we want to model this using tools from thermodynamics, for some of you who might have done thermodynamics, we know that when we have a system at a fixed temperature, then the system has a tendency to minimize not the energy, but actually the free energy. And the free energy is the difference between the energy and the entropy times the temperature. So in some sense, when we minimize the free energy, there's a competition between minimizing the energy and also maximizing the entropy, because we have a minus sign here. Okay, or in other words, it's a competition between maximizing order and maximizing disorder. So you have some sort of competition between having more order and also having more disorder. And this kind of competition is what allows us to have a phase transition. So when we have very low temperatures, then the energy term is winning over the entropy, so we have more order. And when we have higher temperature, above what's called a critical temperature, this is the temperature where there is a phase transition. So for instance, in water at 100 degrees Celsius, that's the phase transition between the liquid to the gas phase of water. The same thing is here. Above some critical temperature, there's a transition to like a disordered phase or a paramagnetic phase, where this phase has, or this phase is in such a case that the entropy term, where there is more disorder, is winning over the energy term. And this is like a disordered phase, and also it has on average a zero magnetic moment, which means that it will not be attracted to magnets, but this one will be attracted to magnets. So those are the two different phases that we will do today in the hands-on session. So I'm going to share also the data set with you. But before doing so, I also wanted to explain to you how we can use machine learning to distinguish between these ferromagnetic phases and the paramagnetic configurations. But before doing so, I want to open the floor, see if there are any questions. Do you have any questions so far? Yeah, if there are no questions, then yeah, let's see how we can do this. Okay. So we've seen last time that we have defined the feed-forward neural network architecture. So we've seen that we can use pictures as an input. Now we can also think of the configuration of spins as also a picture. So the pictures are pixels of spins. So this spin can be down, and the blue one, let's imagine, is spin up. And we can gather all this lattice that we've seen here into a picture. Okay. So this is a new way of thinking of this physical system as a picture that we can feed in to the neural network through this input layer, pixel by pixel. And then it's going to be processed through some hidden layers. And at the output, it's going to predict either that's a paramagnetic phase or disordered phase, or a ferromagnetic phase or an ordered phase. And to do this, we need a data set. So this is something that we can either get from the experiments, or that's something we can also simulate synthetically from some sort of numerical simulation. So this is the example that I want to highlight here from numerical simulations. The experiments case is something that it's not gonna be covered today, but if you're interested, I can share more resources about that. But I'm following here this paper that I'm sure you've seen in the outline of this lecture series. So these researchers have used a data set that's simulated from numerics in order to train the feed-forward neural network to learn about paramagnetic configurations and ferromagnetic configurations. So for the training, we input configurations to the feed-forward neural network, and then basically we hope that we're going to get the correct output. So this is a paramagnetic configurations. So hopefully we have this by using gradient descent optimization. And the way we can do this is, again, by using this mean squared error or some other sorts of cost functions, and by optimizing to the opposite direction of the gradients so that we can get closer and closer to the minimum. And for gradient descent, we can use many variants. And if you try the hands-on session today, you might see that Adam is the best among the others, but I would encourage you to try on your own to see how that goes. And when they tried this in this paper, when they tried to see how the neural network is doing at different temperatures, it was doing very well, at low temperatures. So it gave a very, very good accuracy for the predictions on new configurations that were not seen in the training data. So the data set was split into train and also testing accuracy. And basically, we've seen a very good accuracy here, and also in the middle, they saw something interesting in the sense that it did not get a good accuracy, and this is very good because this means that the neural network is not able to distinguish between ordered and disordered phases. And this is actually what happens physically at phase transitions, where it's hard at this point to know what is ordered and what is disordered. And they also try to plot the outputs neurons, this is the neurons at the output layer for different sizes of the lattice. And they've seen that these, so for instance, the paramagnetic neuron is going from 0 at low temperatures, and it's spiking more at high temperatures, so that's good. And also the ferromagnetic neuron, it's spiking more at low temperatures, and it's inactive at low temperatures. And both neurons meet at what's called the critical temperature. So they found out through the study that it's possible to find the critical temperature of this model by just basically learning the phases of matter of this model. And they also have tried to see why it's working, and they found that the neural network behind the scenes is doing some sort of combination or is doing a linear transformation of the magnetization of the spins or the average magnetization of the spins. And basically that's a good way of distinguishing between the two, because we know that ordered configuration or ferromagnetic configurations are attracted to magnets, and the other ones which have a zero magnetization have the disordered configuration which has close to zero average of all spins cannot be attracted to magnets. So the fact that we have this difference in the fact that the neural network have managed to find this what's called order parameter of the system allowed to this neural network to distinguish between disordered and ordered configuration. So of course, this is a simple example of some model where we already know the physics. It will be good to do this for something that where we don't know the physics, and that's actually something that was done in follow-up papers here for instance, more particularly for experimental data. So if you're interested, you can check out these papers, and I'll be happy to share more references if you're interested. Just drop me a message by email, and I'll be happy to share more resources. And if you're interested to learn more about machine learning for physics or for many-body physics, you can check out these lecture series at Perimeter Institutes on this link, and also these nice reviews about machine learning. And also want to share a few notes about machine learning specifically. So we've seen the feedforward neural networks architecture, but this is far from being comprehensive. There's also the convolutional neural network architecture, or CNNs. So this is going to be part of the mini project. So this is going to be very useful so this architecture has been useful for processing images. And I'm going to also do one example where these convolutional neural network architectures are useful in terms of classifying what's called topological phases of matter. So I can so this is something that I'm going to do in this mini project for those who are interested. And my research is more focused in natural language processing. So I'm interested in architectures like recurrent neural networks and transformers. So this is what I do a lot in research. And there's also other architectures that I also didn't have a chance to cover, but for those who are interested, you can check out these references here that I've highlighted over here. So for visual learners, you can find these videos, resources here. And also for those who are to read in books, these are references that you can check out on this link here. And so this covers the introduction to how we can use machine learning to classify phases of matter. In the second part of this session, I want you to practice all of what we've seen today and also last time. And so we're gonna do this in Google Colab. So let me share my screen with you to the Google Colab. So we're gonna be doing this. So I'm not sure if everyone have received this link to the Google Colab, but let me see if I can share it with you on the chat. So just 1 second. So I'm going to copy the link and copy it on the chat. So I hope everyone has access now to the link. So you'll be able to find this Google Colab that we're going to use to practice on this 2D Ising model. So we're going to basically use a feed-forward neural network to classify the phases of matter of the 2D Ising model. So either it's going to be ferromagnetic or paramagnetic. So before doing so, like, I think it will be good to take a break of around 10 minutes. So we're going to reconvene back in about 10 minutes. So we're going to come back around 6 p.m. 10 minutes, and then we're going to reconvene to do the hands-on session. Okay. So for those who want to take a break, feel free to take a pause. And then for those who have any questions, you can stay here and ask me any question you have about what we discussed either today or last time. Okay. Thanks, everyone. Sure. Yeah. So let me send the link. So there was a question in the chat about maybe an issue with the link. So let me send it again. So this is the link on the chat. If you have a hard time to log in to the to get into the Google Colab, let me know and I can share the link with you. Okay. So I'll be here. But if in case you have any questions, please unmute. But I would encourage you all to take a break, and we're going to reconvene in about 8 minutes. Thank you.
Yeah, hello.
Yeah, go ahead. Yeah.
Yeah, please, I wanted to ask from the layers, the number of layers that a model should have. Does it depend on the data points, amount of data you have?
Yeah, very good question. So since like there is like nonlinearities like in the model, like or in the neural network, it's very hard to know like theoretically what's for each data set, what's the required number of neurons or what's the required number of layers. So it's basically try and error. So you're gonna first try with a simple model with as few number of neurons as possible, and then you're gonna start step by step increasing the neurons until you get to a good accuracy. So a lot of the time we just basically try and error until you get to a good accuracy. Well, does that
As you are training a model, the performance keeps decreasing. So how does that?
Oh, so you mean like for the last example, like in PyTorch last time, or in
Yeah,
general?
using that example.
Yeah, so for last time, like the example like we've seen last time, like for PyTorch, sometimes like you might see this phenomenon called overfitting, where the more neurons you add, the worse the accuracy. So that's why there's always some sweet spots in terms of the number of neurons where you get the optimal accuracy, and then you see a drop in the accuracy again. So it's hard to know in advance what's the optimal number of neurons. It's always good to to experiment until you see this optimal number in your simulations.
Yeah, and I also wanted to ask, when you're optimizing the neural network, is it the same as evaluating it, like using evaluation matrices or something?
You mean like the confusion matrix? Like, is that what you're referring to?
Like MAE and the confidence level.
So this is something I haven't covered, but yeah, there are like multiple metrics for evaluating the performance of the model. So in this Google Colab, so I'm gonna go over this again, but you will see that we're gonna split the data into 3 parts. So there's the train data set, there's the validation data set, and there's also the test data set. Okay. And this way of like splitting the data is going to be useful to evaluate the performance of the neural network. But this is one way of evaluating the model. There's also some other ways of doing it. But this is a great question. Does that answer a bit?
Yes, please. And the last question I wanted to ask,
Sure.
when you were speaking earlier in your presentation, you mentioned that there was going to be an output before you drew the graph for is it going to be the validation or the test that's going to be the output?
Yeah, so this is a great question. So the outputs, so initially what we're going to use is the training data in order to so the output of the neural network is going to be from the training data. And then we're going to validate like this, we're going to validate the results of the neural network using the what's called the validation data. And then after this validation, we're going to test the final accuracy using this test data. So it's going to be like a multiple step process. First, we're going to train the cost function using the train data. And then we're going to like validate the results using these other data sets. So I'm going to clarify that hopefully in the second hour, but I hope that answers part of your question.
Thank you.
Okay, welcome.
Hello, sir.
Yeah, please go ahead.
Please, at the beginning, we came across, or when you were starting, you were talking about the input layer and then the output. And then at the point, you were explaining that we need to use the cross function so that the difference between the input and the output will be minimal. So I want to find out the training data that we are going to use. Is it having the input layer and the corresponding output layer together?
Oh, that's a good question. So basically, like when we have a cost function, we want to minimize the distance between the outputs, like the outputs of the neural network, and the labels that are in the data set. Okay.
Okay.
So yeah, I guess like you said, like the distance between the outputs in the inputs, is that what you said?
Please come again.
So like, did you mean like that we're going to minimize the distance between the outputs and the inputs? Is that what you meant? Just to make sure I'm following correctly. Or something else?
Yeah.
Yeah, so for the cost function, it's actually it's different. Like we're going to minimize the distance between the outputs, which is going to be a prediction on the label. So we're going to minimize the distance between the prediction at the outputs and the label that we already have in the data set. So hopefully today you're going to see this label in the data sets, like in the Google Colab.
All right.
I hope that answers part of your question. If it's not clear,
yes, please.
Tutorial, let me know and I could clarify a bit.
Like what I wanted to know is, we usually split the data into training set, validation, and then testing data.
Yeah.
So within the training set, do we have the input neurons and then its corresponding output layer so that we are going to create the hidden neurons or what?
Yeah, so when we do the training using the training data, we just gather all the numbers at the outputs. We like basically use them to compute the errors on each label and then we average them. We don't need to keep track of the hidden neurons and also the inputs.
Oh, okay.
Does that answer your question?
Yes, please.
So I think we're good to get started. So after the break, so what I want to do now is explain a bit the first part on the training data and also the test data and validation data, since I guess not everyone is familiar with this, and then I think we're gonna be good to go for the Google Colab session after. Okay, so let me first share my slides, and then I'm gonna explain this first part. So just 1 second. You can all see my screen. So last time, like in the first hour, we've seen that in order to define the cost function, we need the data points, right? And we also need the labels that comes with each data point. And basically for each data points, we're gonna get a prediction at the output layer of the neural network, and then we're gonna measure all the errors and average all of them to get, for instance, the mean squared error loss function. But in order to evaluate the performance of the neural network, we need a procedure to do this, and that's what we do here. So that's what I wanted to explain here. So remember last time, like we talked about supervised learning, we had some sort of data sets, X and Y. So what we can do is divide this data set into 3 parts. So I can divide this data set into a training data. So I can call this D-train. And so this will also contain the same elements of a subset of this training data. So I'm going to have X train and then Y train. After that, I'm going to also have a validation data set. So it's going to be made of also elements of the original data set. So I'm going to call these X-val and Y-val. And then I'm going to also have a final data set, which I'm going to call test data set. So this is going to be X tests and then Y tests. Okay, so the question that you might ask now is, what's the proportion of the division? So like, how do we split up this larger data set into these smaller ones? So what we can do is like follow like a general recipe that's used by a lot of machine learning practitioners. So what we can do is divide this into 70% of training data, and then 20% of validation data, and then 10% of the test data. Okay, so we can basically shuffle this data set like by mixing all the different data points and labels. And then so maybe to clarify here, like we're not shuffling the labels, but we're just keeping we're keeping the data points like the same, but we're shuffling the order. And this is going to be helpful so that to make sure that we're getting the same proportions of each population of data points, or let's say pictures or spin configurations in the data. So after shuffling, then we can have 70% in training, 20% in validation, and 10% into testing. And so now, like since we have defined these 3 data sets, then we can use this training data to train the neural network using the cost function. So basically, we're gonna define the cost function C using the D train, like the training data set. Okay, and then after training, we're gonna validate the results using the validation data. So what I mean by this is, so the next step is validation using dval. So what's going to happen is the following. So imagine that I'm plotting the accuracy as a function of the number of training steps. Okay, so I'm going to first get a plot like this for the train data. So let's imagine that I'm using green. So let's consider I'm using green here for the train data. So this is on the train data. And let's imagine I'm using yellow or orange for the validation data. So remember that this data was not seen by the neural network in the training. So this is, so the validation data is a new data that was not seen in the training. Okay, so you might expect that the accuracy on the validation data to be lower. Okay. So what's going to happen is that you'll see something like this. Hopefully it's going to follow the trend, but sometimes you might be seeing something like this where it's going to start increasing and then it's going to stop. It's going to decreasing while this training accuracy is increasing. So what happens here is that you have what's called overfitting. So this is where the overfitting starts and the accuracy on some new and the new configurations start to decrease while the training accuracy is starting to increase. So this is the example where you like when you start, for someone, if they start memorizing something, they're not actually learning about the actual thing, but they're just memorizing the answer. This is exactly what might happen if you have a neural network that's overfitting for the training data, but doing worse on some new configuration. And this is why we use the validation data bits, because it's going to help us to diagnose this overfitting problem. So by doing hyperparameter tuning, using this validation data, we will be able to find some optimal set of hyperparameters that would allow us to get a good accuracy that matches the trend or matches the evolution of the accuracy on the training data. And hopefully once we find these optimal sets of parameters, so again, like just to remind you here, this is to find optimal hyperparameters, or not necessarily optimal, but good enough hyperparameters. And then, like once we are done with this step, then we can use the test accuracy to report the final accuracy of the model. Okay, of like the neural network model. So some of you might ask why we're not using the validation data set to report the accuracy. The thing is, like, if you're using this data set to fine tune the hyperparameters, then you might be overfitting on the validation data. Sometimes you might get a good accuracy in the validation data, but a bad accuracy on the test data. Sorry, here I meant the test data. So the test data is helpful to know what's the actual accuracy of the model without like having an effect, without like kind of overfitting to the hyperparameters. Okay, so that's why we're using these 3 data sets, and that's what we're going to use in the tutorial today. So I'm going to switch back to the other screen. But in the meantime, if you have any questions about what I've mentioned now, let me know before I explain what we're going to do today for the rest of this hour. Any questions so far? So far, so good? Okay, so if everything is good so far, then let me first introduce this problem that we're gonna do today. And then I will let you work on this, and let me know if you have any questions about the implementation. So we're gonna first start with this problem, which is about training a feed-forward neural network to classify the ferromagnetic and the paramagnetic phases of the 2-dimensional Ising model that we've seen in the first hour. And this is based on this reference that you can find over here. So I've also put it over here, like it's called Machine Learning Phases of Matter. So this is the open version. Like in the journal version, it might not be accessible to everyone. So this is the archive version that you should be able to see the results. So hopefully you can use this paper as a way to help you find the solutions to the questions here. So I'm not going to share the solutions. Like they should be all accessible through this reference here. Okay. So first of all, we need a data set. So this is something that's already available. Like you don't have to worry about generating this data set. So it's going to be made of 10,000 samples of configurations on a 30 by 30 lattice. So this means we're going to have 90 spins in total. So this is generated using a numerical technique called Monte Carlo. I'm not sure we have time to cover this part, but for those who are interested, let me know and I can explain more. What I want you to kind of take away from this is that this is a way to generate some artificial data that would mimic the experiments in real-world scenarios. So this data set is made of ones and zeros. So spin up stands for 1. And spin down will be represented by 0. And each configuration will be a vector of numbers that could be either 0 or 1. And we also have another file that corresponds to labels. So labels that correspond to ferromagnetic configurations, or those that are generated at below the critical temperature will be labeled by 0. And those configurations that are at temperature above the critical temperature Tc, then they will be labeled by 1. And these will correspond to the paramagnetic phase, or PM phase. And we also have another file that will going to be useful later for you to do the plotting, which would correspond to the temperature for each sample or for each configuration. Okay, so this is going to be useful for you later. And something I want also to highlight is that you can download this data from this repository. So there's the link here. You don't need to download it on your laptop. There is a way to download this file into Colab. So you can basically replace this file name by XL30 or YL30 or TL30. And these are all these references are basically taken from this paper over here. Okay. And those are the questions that I want you to go through. So those are the 4 questions. And sorry, here there was an error, like there was a typo. But what I meant here by E was actually part 4. So just in case you see here E, like for those who are found out about this issue, like I guess if you use the link again, you'll be able to see the updated notebook. So what I meant here by E was part 4, or the last question. Okay. So what I want you first to do is to run the code and make sure that everything is good, like in terms of logic of the code. Like if you can use this tool Gemini over here, like you can find it here. Like if you have any questions about a line in the code below over here, you can use that line of code. You can use this prompt here to ask any question for clarifications about what's going on in the code. And also what I want you to do in the beginning before starting the tutorial is to save a copy in Drive. So this way you can edit. Like if you start right away, you won't be able to save your changes. So you can first save a copy in Drive. And then after you do this, I also want you to make sure that you're using a GPU. So to do this, you can go to runtime and then change runtime type. Then make sure that you're using, for instance, a T4 GPU. Okay, so you should be able to see this. If you have CPU, then I want you to change this to GPU so that the runtime is much faster. Okay, so hopefully like you'll be able to run this without problems. If you have issues with the run-in, like this notebook on Google Colab, let me know and I'll be happy to help. Okay, but I'll be happy. I'll be here like for the rest of the hour, and let me know if you have any questions or concerns about the 4 questions over here. Okay. And just to clarify, this part is what's exactly allows to get the data from this GitHub repository. So you don't need to download any data. So it's going to be basically downloaded online to this Google Colab. Okay. So let me know if you have any questions, and I'll stick around here for the rest of the hour. And let me know if you have any questions. Thank you. Yeah, so feel free to explore or to like start with understanding what's going on in the code, and I'll be happy to help. There was a question in the chat. Maybe not everyone has access to the code, so let me share the code again with you. So let me copy the link, and then you'll be able to find the link on the chat. Okay. If anyone is struggling with running the code or with getting access to the link, let me know and I should be able to help. Maybe in 15 minutes from now, we can do questions 1 and 2 together. And then for the rest, it's okay if you didn't get to question 3 and 4, but you can take a look at this reference for to get the idea about the solutions. Or you can ask me questions later by contact me through email later. Okay, so I'm gonna post my email in the chat for those who don't have that. This is my email if you have any questions about the topics today or about the content of this Google hands-on session. If someone just joined, let me know and I could also share the link again. I'll be happy to. And if you have any questions, you can unmute yourself and also share your screen if you have any problem with the code. How is it going for everyone? Did you all manage to run your code? Just want to get some like answer from someone just to make sure if everything is good.
Yes, all my codes are done
Good.
running.
Okay, that's good to hear. Thank you for reassuring me. Appreciate it. Okay, everyone. So we're gonna do like question 1 and 4 in about 5 minutes. In the meantime, let me know. You're welcome to ask your questions here, either on a chat or by unmuting yourself.
Yes, sir.
Yeah, please go ahead.
Please, I wanted to ask the backward pass that happens during back propagation.
Yeah.
How is it? I don't really understand.
Yeah, like this is a good question. I haven't covered back propagation. It's slightly like a bit technical. Like I don't want to kind of make it like the focus of this lecture. If you're interested, like I can share some free resources later. But I guess if you check one of the references that I've shared at the end of this lecture on like so there's this deep learning book. So you can Google deep learning book like on Google, like you find it available. And you'll be able to find like one chapter that talks about backpropagation. And there's also like in the YouTube channel that I've like shared like in one of the references if you come back to the recording later. So this channel is very good at explaining how backpropagation works. So sorry I didn't have time to cover this part, but if you're interested, like you're welcome to check out these references to understand how backpropagation works in more details. But in high level details, it basically starts from like backpropagation starts to update the parameters from the output layer, and it goes backwards and updates the parameters in each layer sequentially until we get to the input layer. So that's roughly speaking how that works. The details are in the references if you're interested. I hope that answers part of your question.
Yes, thank you very much. And honestly, I would like to get the link to the video, the YouTube video that explains it.
Yeah, so what I can do, I can share the slides with Dr. Henry, and then he can share those with you later. If would that work for you?
Yes, please.
Oh, sounds good. Yeah, so let's do that. Yeah, so I'll make sure to share the slides with you later. Thanks. Any other question?
Yeah, hello.
Yeah, please go ahead. Yeah.
Yeah, when you
Yeah, sorry, I can't hear you now. Can you repeat it, please? Can you say it
pardon
again?
me.
Sorry. Can you say it again?
When we're talking about optimizing the model, you mentioned using, was it Adam?
Yeah, Adam Optimizer. Yeah. So you'll be able to find it here. Yeah. So
And
there's
it's not in the code, or you're not using that in this class.
So it's a commented part of the code. So you'll find like this called stochastic gradient descent. So it's a variant of gradient descent. And there's also this Adam Optimizer.
Oh yeah. Okay.
So it's commented, so you can just remove this hashtag or sorry, yeah.
Yeah.
Like here, and then you'll be able to use it. And you can also comment this line. And you'll be able to see that there is a big difference when you use this Atom optimizer. And you can
Okay.
also check the references that I will share later to understand how Atom works. So it's a bit sophisticated, a bit more sophisticated than simple gradient descent. That's a great question. Yeah.
Thank you.
But if not, then let me start to do question. Yeah, question 1, like in 2 with you. Just for the sake of clarifications, like you might see something like problem 1D or something like that. This is actually from the previous problem that I've shared with you like last time. I just basically copied the code from last time, and then I adapted it a bit to the classification task that we're gonna do today. Okay, so sorry for that confusion here. So for the first part, basically what you're asking is like making sure that you're understanding everything in the code, not necessarily the fine details, but how that works in high level details. So basically I can do that over here. So basically this first part is about loading the data. So we're using this np.load task text to load these files that we downloaded using these commands here. Okay. And you'll be able to see the files here. Like if you click on this folder, like you'll be able to see these files downloaded to the Google Colab. And you can also check the content by double clicking on them. So you'll see that there's like temperature. So temperature is 1, and then it keeps increasing as you scroll down. And if you also check the other folder for the labels, you'll be able to see the labels. So you'll see a lot of zeros, and then if you go scroll down, after, you'll see a lot of labels with 1. So this is why I mentioned shuffling the data before. So you see a lot of labels like in the beginning starts with zeros, and a lot of the labels at the end will be 1. So it's good to shuffle the data so that you have a mixture between ferromagnetic and paramagnetic configurations. If we take 70% of the data, then we have a lot of majority of the data will be actually basically I guess here label 0 is ferromagnetic. Correct me if I'm wrong here, just from the convention that I've seen, like that I covered in the lecture. So let me just check quickly in the description. Yeah, so label 0 is ferromagnetic. Yeah, so we'll have if we take 70% without shuffling, then we'll have the majority of the data is in the ferromagnetic phase. But if we shuffle, then we have basically an even number of ferromagnetic and ferromagnetic when we do the shuffling here in this part. So you see, like in this part, like we do some shuffling of the indices of the configurations, and then we're shuffling the data. And then after shuffling, then we take 70% of the data for the training data. So this is what we do here for this part. We take the remaining 20% for validation, and then the remaining 10% for the test data. Okay. After doing that, similarly to last time, like for the PyTorch code for the classification of spirals, we define this feed-forward neural network. Something we need to change is the input size. So it has to be N0, which is the input size. So here it's L times L. So that's the total number of spins. And we also need to define the number of neurons in the hidden layer, and also the number of neurons in the output layer, which is 2. We have 2 neurons for each class, 1 neuron for each class. And 4 is just one number to start with. We can start with this number, but of course it will be better to start, to increase that number to get a better accuracy. So here for the hidden layer, we have this ReLU activation, but we could also change it to sigmoid. And for the output layer, we're using softmax. Remember, for softmax, it's suitable for tasks where we have a classification, when we want to predict what's the probability of some configuration to be in a certain class. So softmax is better to use in this context. And then after that, like we're using this one hot encoding that we've seen last time to transform the labels from 0 or 1 to two-dimensional vectors. So that so this is like you'll see in the solutions from the tutorial last time why it's good to use one hot encoding. And here we're defining a learning rate. So a good recipe to start with when we optimize with gradient descent is like a value that's around 10 to the minus 3. And then if you see something like that does not work, then you can lower that by 1 order of magnitude or increase that by 1 order of magnitude. So here we're starting. Also here we're using gradient descent. Like this is the standard optimization that I've explained in the session today. And there's also another like a more advanced version, which is Adam Optimizer. So we're going to start with this, and then we're going to see later how Adam would work. And then here it is the definition of the cost function that's already built in, like in PyTorch. So PyTorch already simplifies a lot of things here. And there's also this other cross entropy loss function that I haven't explained, but you're welcome to use it as well. And for number of epochs, that's the number of training steps, or the number of times we're going to do gradient descent on the feed-forward neural network. So I'm going to run this part, and then the final part is about plotting. So here this was the last part that I have that we have done for the previous tutorial for Spiral. So that's why you see it commented here. I was thinking of having you like adapt the previous code to do this stuff, but I was thinking that might take too much time. That's why you're seeing this here. And also like this is also part of the old tutorial from last time, so I'm sure you would recognize this, but this is not relevant for this problem. That's why you're seeing it commented here. Okay, so this is for the purpose of plotting, and this is for purpose of doing the optimization. So if you run this, then you'll be able to see a plot coming up here, and you'll see that the training accuracy is increasing very quickly, and then it starts to drop. So this means that something went wrong in the optimization. Maybe we need to lower the learning rate a bit or change some other hyperparameters. So it seems that it increased it a bit to 70%, and then it starts dropping and it starts increasing. Okay, so this means that we have to change some hyperparameter in the code. So maybe what I could do is increase the learning rate a little bit. So I could do maybe 50. So let me rerun this cell and then rerun the training again and see if this is going to improve. Okay, so it seems that maybe the number of hidden neurons was not enough. Okay, so sometimes when you see something like that, it's good to increase the number of neurons to something that's higher. And here you see that the training accuracy is increasing a bit more. And what I want you also to do here is plot the validation accuracy as well. So here there is also only the training accuracy. So what you could do is plot the validation accuracy along with the training accuracy and see if it has a similar trend. And then at the end, plot the test reported test accuracy by running this final part. Okay. So this is something I would want you to do, like for the remaining part of this tutorial for those who didn't manage to do it. And also I would encourage you to try also this other optimizer. So if I run this one, you'll be able to see that it's actually doing something much better. So it's going closer to 100% accuracy right from the first 500 gradient descent steps compared to the other. So it's really amazing how this optimizer works compared to the plain gradient descent optimizer. Okay, so this is a brief overview over the first two questions of this.
Sir.
Yeah, please go ahead.
Kindly go over what you just did, please, where the accuracy almost reached 100%, please.
Yeah, so this one, like the accuracy, so this is the train accuracy almost 100%, right?
Yeah, it seems you did something before. I couldn't get that.
Sorry, yeah. I basically changed this gradient descent optimizer to Adam optimizer. So it was like that before, and then I just commented this and used this line.
Okay, it's very clear now. Thank you.
Yeah, it seems that this optimizer kind of dramatically allows to get a better accuracy. But this spot is only for the train accuracy. I also want you to add the validation accuracy here as well. Okay, so this might require a bit of change to this code. So I trust you to try this later, either today or after the session. You'll be able to see, hopefully, that the validation accuracy is also following the same trend as the train accuracy. And then after doing this, after finding the optimal sets of hyperparameters, you'll be able to run this cell where you'll see that the final accuracy here is like 94%, which is lower than you would expect here. So here it's close to 100%. So it's clearly that the model is not be able to generalize very, very well. So we need to do some sort of further tweaking to make it even better. So, so this is something that you could do and explore later, after this session today. And as I've mentioned, you're always welcome to send me your questions through the email that I shared over the chat. And this is far from being like comprehensive, like for this, what's going on in this field. This is just an introduction. And if you're interested, like you're welcome to sign up for the mini course that we're going to start in October. So we're going to learn more about convolutional neural networks and also about other classification tasks in terms of classifying topological phases of matter. So if this is of interest to you, like I would encourage you to sign up for that. And if you're interested in other things related to machine learning, like please feel free to send me your questions, and I'll try to get to answer your question whenever I have time. Okay, so it was a real pleasure to meet everyone today. Before ending the session, I want to open the floor for anyone who has a question about the notebook or the tutorial today. Anyone has a final question? Okay, so if not, then I thank you all for all your great questions, and also for kindly having me in this lecture series. It was a real pleasure to be here. And I wish you all the best in your future endeavors. And please keep in touch and let me know if you have any questions. And I'll be happy to help. Okay. Thanks very much, everyone. It was a real pleasure to meet you. Thank you. Yeah, for signing up for the mini course, I think you can ask Dr. Henry for more details. Hopefully, yeah, he'll be able to clarify that. Thank you. Thanks very much, everyone. Yeah, wish you a great rest of your day, and let me know if you have any questions later by email. Thank you.
Okay, thank you very much, Mohamed, for this session. Also thank the participants for joining for this session, and you've covered quite a lot of important aspects in machine learning and physics. So I hope they'll continue to practice, whilst we also try to cover some of the lectures that we have in the preceding. Okay, so for the talk, we'll have it available on YouTube within the week, so you can go back and get access to what we did today. We also have the previous one that's over there, and I think you have access to the notebook, but we'll post it into the my class so that you can have access to the notebook and practice. Okay, so for the mini course, Dr. Martin will send you a message on that and how to register for the mini course later on within the week. Okay, so thank you very much, everyone, for joining, and hope to see you again. Bye-bye.